Optimization problems, which seek to minimize or maximize a real function, play an important role in the real world. It can be classified into unconstrained optimization problems and constrained optimization problems. Many practical uses in science, engineering, economics, or even in our everyday life can be formulated as constrained optimization problems, such as minimization of the energy of a particle in physics, how to maximize the profit of the investment in economics. Lagrange multipliers method. In this section, first, the Lagrange multipliers method for nonlinear optimization problems only with equality constraints is discussed. The mathematical proof and the geometry explanation are presented. Then the method is extended to cover the inequality constraints. Without the inequality constraints, the standard form of the nonlinear optimization problems can be formulated as minimum function of x sub 1 to x sub n, subjected to the function of g x sub 1 to x sub n is equal to 0, where g is the constraints function vector. The Lagrange function f is constructed as the Lagrange function of x and the function of proportionality constant lambda is equal to the function of x minus the proportionality constant times the gradient function of x, where x is equals to x sub 1 to x sub n. The variable vector lambda equals to lambda sub 1 to lambda sub k are called Lagrange multipliers. The extreme points of the f and the Lagrange multipliers lambda satisfy gradient of f is equals to 0. Lagrange multipliers method defines the necessary conditions for the constrained nonlinear optimization problems. Application to the power system's economic operation. The Lagrange multiplier method is widely used to solve extreme value problems in science, economics, and engineering. In the cases where the objective function f and the constraints g have specific meanings, the Lagrange multipliers often has an identifiable significance. In economics, if you're maximizing profit subject to a limited resource, lambda is the resource marginal value, sometimes called shadow price. Specifically, the value of the Lagrange multiplier is the rate at which the optimal value of the objective function f changes if you change the constraints. An important application of Lagrange multipliers method in power systems is the economic dispatch or Labla dispatch problem, which is the cross fields of engineering and economics. In this problem, the objective function to minimize is the generating cost, and the variables are subjected to the power balance constraint. This economic dispatch method is illustrated in the following example. Three generators with the following cost functions serve a load of 952 megawatts. Assuming a lossless system, calculate the optimal generation scheduling of the three functions given. Where x sub I is the output power of the generator. F sub I is the cost per hour of the generator. The cost function f sub I with respect to x sub I is generated by polynomial curve fitting based on the generator operation data. X sub I has the unit megawatts, since W equals J divided by S, and the cost to produce 1 joule has the unit peso. We have the equation. Hence, the cost f sub I has the unit peso per hour. The first step in determining the optimal scheduling of the generators is to express the problem in mathematical form. Thus, optimization statement is f equals function 1 plus function 2 plus function 3. Substituting the given, we come up with subject to g equals x sub 1 plus x sub 2 plus x sub 3 minus 952 equals 0. The corresponding Lagrange function is setting gradient f equals 0 and yields the following set of linear equations. First row, 0.125, 0, 0, and -1. For row number 2, 0, 0.025, 0, -1. For row 3, 0, 0, 0.05, -1. And for the last row is 1, 1, 1, and 0. Multiplied by x sub 1, x sub 2, x sub 3, and lambda, which will equals to -1, -1, -1, and 952. Solving g equals x sub 1 plus x sub 2 plus x sub 3 minus 952 equals 0 yields x sub 1 equals to 112 megawatt, x sub 2 equals 560 megawatts, x sub 3 equals 280 megawatts. Lambda is equals to 15 peso per megawatt per hour. And the constrained cost F is 7,616 peso per hour. This is the generation scheduling that minimizes the hourly cost of production. The value of lambda is the incremental of break-even cost of production. This gives a company a price cut-off for buying or selling generation. If they can purchase generation for less than lambda, then their overall cost will decrease. Likewise, if generation can be sold for greater than lambda, their overall cost will increase. Also note that at the optimal scheduling, the value of lambda and x sub I satisfy the following equation. Since lambda is the incremental cost for the system, this point is also called the point of equal incremental cost criterion. Any deviation in generation from the equal incremental cost scheduling will result in an increase in production cost F. In summary, the Lagrange multipliers method is a very efficient tool for the nonlinear optimization problems, which is capable of dealing with both equality-constrained and inequality-constrained nonlinear optimization problems. Many computational programming methods, such as the barrier and interior point method, penalizing and augmented Lagrange method, have been developed based on the basic rules of Lagrange multipliers method. The Lagrange multipliers method and its extended methods are widely applied in science, engineering, economics, and our everyday life.